Thank you, everyone, for joining the July version of the Liftoff webinar series featuring the Coldwater Machine Company. This is Joe Steele from Lift. Luckily enough, coming to you live from Coldwater, Michigan today. So thank you very much for taking time to join us. The Liftoff webinar series was put together by Lift, Lightweight Innovations for Tomorrow, one of the Manufacturing USA institutes, along with the Michigan Manufacturing Technology Center, and we put this together in an effort to feature those small and medium-sized manufacturers who are coming up with lightweighting innovations that we wanted to highlight. So we're lucky enough to have Coldwater Machine Company with us today to talk about friction welding advances and applications. There's a few housekeeping items I'd like to tackle before we begin. However, if you haven't already, please put your phones on mute so we don't have any background noise when the presentation is going on. If you have any questions, please use the chat function. It's part of the GoToMeeting menu on the side of your screen, and you can address the questions to the organizer. Those questions will then come to me, and I will facilitate the Q&A at the end with Mike. And finally, each of these Liftoff webinars are recorded and are posted to the Lift website for future viewing. So if you had folks that wanted to join us but couldn't join, or you wanted to share it with somebody, you can certainly do that later on once we post it. We try to post these by the following Monday after the Thursday they occur. So a little bit about Lift. As I mentioned, we are a member of Manufacturing USA. There are 14 of these manufacturing innovation institutes around the country. Each of us has a focus on different technologies, and Lift's focus is on lightweight metals. Our goal is to revolutionize lightweight metals manufacturing through innovation and education. We really have three, pillars in which we operate. That is technology development, the R&D that we are undertaking. We have a number of R&D programs in our portfolio. You can learn more about those on our website at lift.technology. We also want to transition that technology and those R&D findings. What good is finding a new solution to something, a new lightweighting solution, if we don't transition it into the marketplace? So we certainly want to work with companies to do that. And then we also want to make sure that there are people with the skills and abilities to work with those new innovations and new technologies when they do get in the marketplace. So we have a large education workforce development side of our operation. We've invested in over 40 education workforce initiatives to refill that pipeline of talented workers to make sure that that manufacturing is robust and re-energized in the country, which is the goal of all of the Manufacturing USA institutes. We are sponsored at Lift by we're a public-private partnership sponsored in part by the Department of Defense, as well as all of our industry members and academic members. Of the 14 Manufacturing USA institutes, 8 of them are sponsored by the Department of Defense, 5 of them are sponsored by the Department of Energy, and 1 is sponsored by the Department of Commerce. You can learn more about Manufacturing USA at manufacturingusa.com, or you connect to Manufacturing USA right from our Lift.technology website. You can also follow us on Twitter and at News from Lift. You can also follow us on LinkedIn and Facebook as well. Also wanted to note, within the last month or so, we've named a new CEO and executive director, the former auto czar of the state of Michigan, Nigel Francis. So he is busy getting his feet wet, having taken the job about a month ago. So I'm sure you'll be hearing more from him in the future as we go forward. A little bit about our facility in Detroit. We share space with one of the other institutes, the Department of Energy Institute, called IACME. They focus on composite materials, so we have lightweight metals and composites in the same place. The equipment we have online, you see on your screen here, from a large extrusion press to a hydroforming press and a stamping press to a very large multi-robot joining cell. So any of the services you see on your screen, plus some, we'll be able to offer you. So please contact us online, or you can give us a call, and we'd be happy to work with you and get your lightweighting projects underway. I mentioned that these liftoff webinars are brought to you by LIFT and the Michigan Manufacturing Technology Center. I don't know if I have anyone from MMTC online, do I? Hearing none, it sounds like they were unable to join us. I will mention that the center is part of the Manufacturing Extension Partnership through the National Institutes of Science and Technology in Washington, D.C. Every state has an MEP, a Manufacturing Extension Partnership. The center is ours here in Michigan, and they are geared towards helping small and medium-sized manufacturers of any kind, from, doesn't have to be lightweight metals, could be food, could be a manufacturer of any kind, with cybersecurity, with accelerating their technology, with doing some research, any of that. So they are located over in Plymouth, Michigan, suburban Detroit, and you can contact them at thecenter.org. We've had some projects with them. We gave a presentation last month, actually, on the Liftoff webinar series about one of the projects that we have with them, a lightweight auto frame that we've been creating with them, or have created with them and some of our partners. So please go back and watch that. That is posted on our website, or you can reach out to them directly at thecenter.org. But without further ado, I know you guys did not come to hear from me. I know you came to hear from Mike Spodar of Coldwater Machine Company. Mike is the senior welding engineer for Coldwater Machine Company. He supervises the Solid State Joining Center and the Metallurgical Laboratory for Coldwater. Mike works directly with industrial customers to develop new applications for both rotational friction welding and refill friction stir spot welding, I should say, processes. He's got an extensive background in joining both ferrous and non-ferrous materials, utilizing plasma welding and robotics, as worked for Hobart Brothers, Arvin Meritor, and Lockheed Martin, and holds a BS in welding engineering from The Ohio State University. So with that, I will turn it over to Mike, and we'll hear about the friction welding advances and applications. So Mike, I'm going to give the presentation over to you.
Well, thanks to everyone. I'd like to thank you all for joining us today. Appreciate your taking this time. I know some of you are at lunch, so I hope this is worthwhile for you, taking some time out from your lunch. I am Mike Spodar. I am the senior welding engineer for Coldwater Machine, and I'd like to give you just a little background on the company. We were started about 60 years ago by 3 tool makers. Over the time, we've grown to over 120 strong workforce with approximately 30 engineers split between mechanical design and electrical controls. And then we also have about 45 skilled trades on the floor for building and assembling. We are split between, say, build to print with a lot of precision machining on the floor, and then also we just expanded our production floor to allow for larger and longer assembly and fabrication lines. So this is a photo of the shop looking down from the new expansion out on the floor. We've been involved in friction welding since about 2003. At the time, mostly rotational friction welding, and we have been involved as a member of LIFT since near its inception, and we've participated in events on their floor and in their projects. So part of the day, we'll talk about some of the challenges the industry faces and how do we address that. We work with a lot of automotive customers, appliance customers, energy customers. So while what you see on the screen right now might be an automotive assembly line, we see that all the other industrial segments will face one of these challenges, and we would like to help address some of those questions. So to start basically, friction welding is inducing a weld through a method of friction and force. There are different types of friction welding. One of the earliest and oldest was rotational friction welding, where we're spinning at least one part against another part and applying a direct force. Over time, that's grown and evolved to other features. For example, linear friction welding is moving one part, say, laterally in relation to the other part. Lift will be getting a large cell a little later this year, which will be a linear friction welder. It will be a large machine capable of 35 tons of oscillating force and up to 75 tons of frictional force. So they will be able to put together a large component directly on their floor. But it can also be an orbital weld where one part is moved in a circle rather than spinning the part. There is now linear stir friction welding where a solid tool is used as the parts are butted up against each other to create a nice butt weld. And then one of the latest has been friction spot welding. So in this case, we have a tool that is rotating and we'll go and make a spot weld between some parts that are in a lap joint configuration. So some of the benefits that we see from friction welding are with the rotational or orbital or linear friction welds. We can join dissimilar materials since we're not necessarily melting the parts. We're getting up to a very high temperature and into a plastic state. We can then forge these two parts together. We aren't going to an elevated temperature, and a lot of times we can keep our friction times low, so we will have a low or small heat affected zone. Typically, we don't use any flux or filler wire, and while shielding gas is not required, we have welded in the past some materials that did find an advantage with shielding gas. But as it is a solid state process, we do not have typical weld defects such as porosity. This is kind of a picture of the setup in the lab. What we have is a weld head, and in the middle would be the part we are rotating. In this case, we are holding a round part or a tubular part in a collet. And then we would spin that part against the base part or the bottom part. This would be the stationary part. You can see we just have it chucked up in a 3-jaw chuck right now. The part would be spun, and what happens is as material starts to heat up and we start applying force, the material will start to flow, and that develops some weld flash or curl or results in a part upset. So one thing we need to consider when designing parts for friction welding is that there will be a loss in the length of the material, and we need to typically add that to the parts that come to us prior to welding. Yep. So friction welding heads come in many sizes. They can typically be installed as a machine or on a machine. It's a relatively safe process, and a lot of the mechanical energy is transferred directly to the parts as heat. Typically, the only utilities require would be an electric drop, some shop air, and then typically the weld heads are water cooled. Through AWS, they provide a large list of parts that in the past have produced good results with rotary friction welding. And then we also are developing a chart for combinations of friction spot welds. And while the chart is extensive, it's by no means absolute. So we do a lot of development and trial and error runs with customers to validate new parts or new materials that they would like to join. And a lot of times we'll do that. We'll just say they'll send them some parts, 5 or 6 parts. We'll we'll see that they actually bond, and then we can develop a larger test regimen for more extensive trials. So we've kind of taken the moniker of SpinMeld for our rotary friction welding, and to give it a more detailed talk, we hold one part stationary, we spin the other part at a high rate of speed. As they come together, they start generating heat, and we need that to radiate across the face of the weld. And as that happens and they start applying pressure, the materials start to flow, and they will flow out. With our direct drive system, we can either let that slow down in a natural reduction in RPM, or we can break it, and that gives us an immediate stoppage. And then you'll see the representation of weld flash here. What's important to note is that the weld flash will always go to the outside, but if you would see a tubular section, you would still see flash on the inside and the outside of the tube. So we have had applications where we've had to clean up the ID of the part after a weld. There are different, while the process is the same, there are different, say, applications, such as tube to tube, tube to bar to bar, plate to plate, and plate to tube. Once again, there will be a reduction, but most of the time this will come directly from the rotating part rather than the stationary part if it's a plate. A bar to bar, bar to tube would typically show part reduction or weld flash in both specimens. So our weld heads are electric, and they are direct drive machines. And some of them have the ability to clock the part for pickup and also for final position. So that's been important for some applications where we can hold the final part to a plus or minus 1 degree location. A lot of times we're going in, we're competing or replacing a drawn arc stud or a projection weld, or even some cases a part that's going to be MIG'd or TIG weld in place. And a lot of our early development will be taking one of those parts and showing that we can duplicate the results and improve the process with our weld process. So a lot of times we are then able to work with the customer to change the design slightly so that it's more amenable for friction welding. It's nice to be able to have some type of feature on the part that we can actually say hold and grip to impart the friction or apply it, or else we need a face with which to say forge or press against the other part. Some of the quality aspects are that we do have a very good repetition to our weld system. It can create leak-tight or airtight joints. We typically don't have a huge coarse grain zone because we do have a typically short friction time. One of the things you see here was this is a steel stud to a 1-inch diameter steel tube. The wall thickness here is about 80 thousandths. And what you can see is a slight bulge on the ID of the tube. That's from the force of the friction weld. So sometimes we're asked if we can weld to a tubular structure, and we have to say, kind of depends, because the steel tube was stiff enough and strong enough to support the forces from the weld. But other times, if we're looking at a thinner tube, or if you're looking at a different material, it might not give us the same results. Some of the things that can be done, though, would be to insert a mandrel into this tube before welding, create the weld, and then slide the mandrel out, and you'd have a very smooth surface in here. Some of the key features to this would be the fusion line here, your heat affected zone, but also you can see some weld material caught up in this cavity here. And this was by design. This stud that was welded in place has basically a little skirt that goes around the outside to hide the weld flash and just really improve the appearance of the part after final welding. With the friction welding equipment we have, we do have good documentation and process control. And what you can see from this chart, which would be our process monitoring system, the red line indicates the RPM, so it starts off at a high level and then drops off. The yellow line would be the force, and then the green line would be the position of the part. With friction welding, there is typically a friction phase and a forging phase, and you can kind of see that on this chart here. The friction phase would be this portion here where we're applying friction and force, and then we go into a brake function which slows down the RPM and go into the forging phase where we increase the forge pressure. So that will help fuse and solidify the two parts together into a solid piece. Some of the things that you don't see on this screen but are reported on the operator screen will be some of the best part parameters for checking the consistency of your welds. So we get a part contact reading and we get a part reduction reading. And what you can use these for are to verify that, number one, your target is in the correct position, it hasn't been double stacked or is missing. And then with the part reduction, you should get a consistent value saying that you have, or showing that you get a consistent weld. So we're talking, say tenths of a millimeter repeatability to indicate a good acceptable weld. And I'd like to point out that these are really the only three variables for the process. And if you're familiar with resistance welding, then you can kind of equate the resistance welding parameter sets of current pressure and time with our RPM pressure and distance. A different way of using the process is, in this case, spinning a small rivet. In this case, it's through a sheet of aluminum and to some hot stamped boron steel. And this way, we're more or less riveting the aluminum sheet to the hot stamped boron steel. This works out well, and since the hot stamped boron steel is a difficult material to join to typically, it's offering us some unique answers. But the rivet will have to be sized for the thickness of the plate or the material that you're going through. I do have a video here that we can run to kind of give you a flavor of friction welding. For us, this was a big part and a long friction cycle, and we'll let it go. So this is not a production weld. This was some development work happening in our weld lab with some 1-inch material. This is an Inconel to stellite. And some of the unique things you can see here are that we're really only getting curl on one part, in that the Inconel was the only part that was showing any type of part upset or weld flow. The other thing was that the stellite cut at a slight angle, so we had to increase our friction time to ensure that we got a good weld all the way across that fusion line. And then you can see the effect of the heat on both sides of the weld, leaving a little heat affected zone trail there. But that was a good indication of what we can do with dissimilar materials. Once again, that was an inconite to stellite. You don't see a lot of that in production, but it does show some unique capabilities. This part here, for example, is actually a powdered metal fitting to a steel stamping. These components over here are parts that were friction welded. This is a silver tab to a copper bar. So you can see this is the original copper bar. This is the silver tab welded in place with some weld flash. And then this part has been trimmed of the weld flash. These are just some forms, and some parts are weld trials and some parts were production welds. For example, this part in the corner is an automotive part that's aluminum nuts to aluminum plate. We built a weld cell where the operator would put this plate down on the machine. It would slide into the machine, weld the 3 parts, and slide back in 20 seconds. This was another production part. This is an aluminum tube to an aluminum channel. And kind of the unique thing is that because it is a large diameter tube with a thin wall, we'd like to have something to drive. So we came up with some lobes or ears that we could create a tool to hold those and weld that into place. This is an example of that tube to tube. You can see some weld flash here. If you can imagine, there's weld flash equaling that on the inside. This is kind of unique in that this was a rolled tube with a seam, and also unique in that typically we're going to spin the round part against the square part, but due to the diameter of this, it was quicker and easier for us to take a square block, bolt it to the welder, and spin that. So this case, the block has been spun against the stationary tube. And one of the nice unique things was we did get a nice amount of weld flash and weld curl, but we did not get the seam to open up at the joint. This tube, it was actually a nut to bar stock, kind of large for us, but it does show a carbon steel to stainless steel to carbon steel joint. What we have here is a stainless steel stud to an aluminum channel. So that is a possibility for more dissimilar material joining. This was aluminum tube, and actually some of the development work for number 3. Early on, we cut some notches into the tube to use as say teeth to engage our drive or spin unit. And this is a production part. We do some limited volume, low run parts here. So we do some of this welding for a customer of a long shaft to a round plate. Our niche at Coldwater Machine with rotational friction welding is that we have very high-speed machines with a little lower force. So they go up to about 23,000 RPM and can provide anywhere from 2,000 to 14,000 pounds of force. So in that case, our niche in welding is going to be, say, a diameter of around 2 millimeters and then up to about 2 inches. Plate-wise, we can probably do around 50 thousandths of an inch thickness for a plate. If you want to send in samples, we would ask typically that the part that we would spin be a minimum of 25 millimeters in length. That's just so we have something we can hold and also use to develop parameters that will give us how much part reduction we can expect. We can hold parts as long as 5 inches if necessary. In a completely automated cell, we can produce a weld in about 7 seconds or less if the part is fed in and if the other part is fed in also. And then we can do capability studies or cross sections to ensure we're getting good welds. So friction weld parameters and weld recipes are based on RPM and time and force, and then we split those into typically at least 2 line recipes for RPM, friction time, and friction force would be one line, and then the other line would be forge time and forge force. We can have a friction time as short as 0.05 seconds or as long as 36 seconds. Some of the things that will affect your weld, though, are how flat your welding surfaces are, how smooth or how rough they can be. And then we're also affected by any particular changes in the material, if it is a material change or just a significant change in, say, hardness, and then surface oxidation, if there's something unique or particular to the surface. We can account for that either by going through increasing the friction time or the friction force to kind of ensure a better or improved weld. To show you a few things on the picture here, this is one of our standard weld heads, and it's on in the back there's the machine base. That's kind of the standard configuration, and we can arrange that to then weld parts for production. So in this case, this head is on a standard holder. In this case, it's bolted in place over a servo rotary table, which would have, in this case, it had 4 welding positions. But in other applications, we can put this head on potentially an X slide or even an XY slide to get to several locations over a stationary part, or if this part is moving, then that can also be on an XY. So we can hit multiple locations with one head. The other thing to consider is that we will need a barrier around the cell, just for safety. Typically, we're using a clear plastic, but we can use, in the past, have used steel sides. But it does need to be some type of solid wall there. A light curtain typically is not sufficient to pass a safety audit. We need something to protect operators from any type of, say, flying debris in case a weld head should break or part fly out. It doesn't happen. We like to design that not to be the case, but we still have to plan for the safety considerations of such an event. Let me go back here for a second. For the weld head, the part that we spin, we can do that either with an automated collet, which would be controlled by the machine to open and close before and after the weld, or we can develop a specialized tool for your particular part to grip and hold the part and then release it after welding. So we have 4 standard weld heads with 2 systems. You can see an RSM 401 and then the 410. The 500 is based on the 410, just a larger machine. The smallest, lightest machine goes up to 23,000 RPM. It's only 1.8 kilowatts, but it's really for smaller materials or lighter weight materials, something that's really only about maybe a ½ inch in diameter. We get a little bigger with each machine having a little bigger cross section that it can weld with a lot more force. Once again, there can be up to 3 friction phases that can go up to 36 seconds of total friction time. The unique feature of these last 2 machines is that we do have an angle control, so we can pick up a part on a particular angle if necessary, and then we can stop the weld on a particular angle also. So some customers have found that unique capability to be valuable to them. If they have a unique feature on the part that's spinning, then we can repeatably get it to a location about plus or minus 1 degree. That kind of brings us to the second form of friction welding we can talk about today, and that would be the friction spot welding. So friction spot welding, there's 2 types to talk about really. There's a non-refill friction spot welding, and then there is a refill friction spot welding. So today I will talk about the refill friction spot welding and some of the advantages of that. This would be a picture of the spot weld head. There is an anvil and then a tool set here, and it's similar in form to a resistance welding gun. So this process can weld basically all of the aluminums, 1000 series to 7000 series. Magnesiums have had very good results with magnesium welding. And then we can also do some dissimilar materials with this, but typically it's going to be an aluminum over a different material, so an aluminum over a steel or an aluminum over magnesium. We can do, it says flexible sheet sets, and what that means is we can do with the same tool set a 2 millimeter over a 1 millimeter, a 1 millimeter over a 2 millimeter over a 3 millimeter, and we're just changing the weld recipe for that. We can join up to, say, 4 or 5 sheets, provided they fall within the thickness range of our tool set. I think we have a short video here, and we'll kind of see some of this in operation. It's not much to see other than the open and the close, but that is the operation. It's slowed down a little bit by the process, by the video, I think. This kind of gives you a representation of what's going on. There's a clamp, a sleeve, and a pin. The sleeve goes through the top sheet and then displaces some material to the center, and then we reverse the process of that pin. We'll push that material back down and create a flat surface on the face of the weld. So, no. Lost my spot. So some of the benefits of this is that that weld head can be mounted as a pedestal, or in other applications can be mounted as on a robot. It would be consistent with a resistance welding robot. And as the jaws close, it will close the parts we're welding together. So, sometimes the part fit is not as great as it needs to be with a laser weld, where we need a very tight fit. It is pretty highly energy efficient. We're only providing electro power to the control servos, and then we do cool that weld tool and the anvil. Here's an early example of some of the things we did. In this case, we've got 3 sheets of 6000 series material, 1, 2, 3. Those are 3 millimeters thick, and then a 1.5 millimeter 5000 series sandwiched in there. So that's a total of 10.5 millimeters. In this case, we programmed the sleeve to travel down 7.7 millimeters. So about right here, you can see that interface. And typically that's all we need is about 0.2 to 0.5 millimeters of getting that sleeve into the bottom sheet to create a weld. And then you can see, you know, the effects. We have swirled those three materials together to create a weld. We do get a report from this process, and you can see here a screenshot of that graph. So red line indicates the RPM of the tools. The dark green line indicates the pin position. The dark blue line indicates the sleeve position. And then the light lines are the current going through the motors for the pin and the sleeve. These charts are generated individually and are stored then individually. So just kind of wrapping up here. This is some photos taken in our weld lab. We have one friction spout melder mounted to a robot. It's in a large enclosure, so we can and have done large panels and body components in the past. We have one on a pedestal, so we can do some quick coupon work there. On the other side of the door, not letting you see that, this photo is inset of the lab back there, showing one of our welders and another head on the stand. Our two welders are on the other wall. But with this with table and feature here, we can mock up a lot of your welds and do a lot of part demonstrations. We do have a 2-ton hoist in the lab that comes in handy either for moving parts or fixturing around. We can do simple tests in the lab, bend tests and tensile tests. We have a small metallurgical setup for doing cross-section evaluation. Typically what we're doing in the lab is developing the weld sets, the weld parameters to show the process capabilities. We can also help with modification of nuts and studs to make them more amenable for the friction welding process. And as I said, we can do some low volume, short-term production in the lab. So getting kind of short for time here, I think. So just like to say thank you and appreciate you taking the time. And I think I'll turn things back over to Joe for the conclusion. And if there's any questions.
Thank you very much, Mike. Yeah, there actually were a couple of questions that came in, so we do have a little bit of time. Remember, if you do have a question, please use the GoToMeeting taskbar. For me, it's on the right side of the screen, and just address it to the organizer, and that'll come to me, and we can facilitate the Q&A. But a couple of questions that came in initially, Mike. Has a SpinMeld joining a rod or tube inside the diameter of a dissimilar metal tube been performed to produce a superior metallurgical bond alternative to shrink fitting? Mike, did we lose you?
Sorry. Hello?
Oh, there you are.
Yeah, sorry about that. Yeah, I haven't seen that been in producing acceptable welds because we don't have a direct line of force then. What happens if you try and spin something inside of another thing is the material will just start to flow away, and because we can't contain it with a direct force, we haven't been able to produce an acceptable weld.
All right, thank you. And if you, by the way, if you are interested in receiving a copy of this presentation, I will defer to Mike on that and refer you to Mike on that. Mike, there may be some folks that ask you, but I remember these webinars are posted on the lift.technology website in video form, so you can certainly direct people there as well. Mike, is friction joining a ceramic to a metal feasible to produce a hermetic seal?
Ooh, that would be an interesting one to try. I don't see the ceramic being a part that would flow. So we would need to get the metallic part to flow against the other one and bond. So it would be an interesting challenge and something we'd like to try, sure.
All right, very good. Has friction welding been performed on metal matrix composites at all? They're a composite of metal with ceramic strengthening phase.
Yeah, I want to say they have been in some applications. I don't have an experience with that. We've tried doing some joining of carbon fiber to aluminum or other material. We've had some limited success with that. It starts introducing some galvanic corrosion almost immediately. So depending on the form, it might be possible with certain precautions.
Getting some good questions here, stumping you almost. Regarding the spot weld, the spot experienced material loss and is lower than base material. How low is it relative to the pin diameter?
If you're talking about the face of the weld, low in reference to your base metal, what we try and do is balance and program the pin in the sleeve to actually create a weld that is even with the top of the sheet. So, sometimes we have to do a little manipulation of the tools to ensure that we get a flat weld and a face of the weld that's even with the base metal that surrounds it. I think there was a second part of the question about material loss inside the weld itself. And typically what we look at is, as we put the tool set in and we create some validation welds to level off our tools, we get some material that transfers inside the tools, but then it also will transfer back in subsequent welds. So I don't see a significant amount of material loss in the sections of friction spot welds.
This is actually one I was thinking about as well. Regarding the tube weld, how does it look inside the tube? Is there too much extra, material flashing inside as well?
It will be, if the sizes are the same inside and out, then the weld flash that appears on the outside of the tube will be similar to what's on the ID of the tube. So there will be some material in there, but not significantly more than what's on the outside.
And then how do you cope with with the deformation, if there is any?
Well, it depends, in some cases what the application is. We were talking to a customer that was trying to lightweight their solid rod by joining, two ends to a tube. So for them, they really didn't care what the inside of the tube looked like. That weld flash would then remained inside their product. Weld flash is always kind of something the customer needs to determine if they're going to remove or leave in place.
Okay. Earlier in the presentation, you mentioned that you didn't use or need any filler materials. But have you done any work to suggest that it might lower cycle time or increase the mechanical attributes?
No, we have not done anything like that. At 20,000 RPM and about 2,000 pounds of force, it might be difficult to get something to adhere between the two surfaces. I would expect it might be expelled rather than become part of the joint itself. You know, it would be more common for us to say have two materials that do not weld well together, but find an intermediary part that both parts join to, in which case we would weld, that's, you know, basically part one to the intermediary part, which would be a thin layer, and then weld the second part to that subset.
All right, I think we have time for probably one more. I want to be sensitive to folks' time. For aluminum components to be welded with linear stir welding, what is the maximum allowed gap to have an acceptable weld?
I really don't think there's any good acceptable gap there. Typically, those joints are pretty tight, and then the tool is forced into that joint and then translates along it. You know, as that gap increases, then going back to that other question earlier, there will be a loss of material, and you can have some lack of fusion or just a split at the seam.
But we have one more.
Yeah.
Surface definition for spot weld of thin sheet material could be a major challenge. Is there any idea on how to reduce that?
I missed the first part of that.
The surface deformation for spot weld of a thin material.
Thin material.
It's a hurdle. Yeah. You know, in cases where we're going up against, say, a resistant spot weld, our process has typically been better because we're not heating up the material to a melting point and then having it re-solidify. Our weld strengths are typically better than any resistance weld we've compared it with, and some of the surfaces on a resistance weld have, you know, shown deformation and some evidence of depression there. So we'd like to be able to control the face of the weld by our home position of the sleeve and the pin, and sometimes it has to be reset after the tools are cleaned. Got it. Well, I appreciate everyone taking the time today. Mike, thank you so much for your presentation. Again, this presentation will be posted back on the Lift website early next week. Stay tuned for our next Liftoff webinar coming on the third Thursday of August. We are here the third Thursday of every month. I encourage you to reach out to Coldwater, to Mike, and Dan's name is on the screen right now. With any questions, encourage you guys to do business with them. And again, thank you very much. Have a great rest of the day, and we'll see you next month. Thank you.
Thanks, everyone.